היי, אני שנייה בעברית, אז אני אעבור לאנגלית. נתחיל באנגלית. Before I introduce our speaker for today, one quick word. I encourage the students to ask questions. Adar is a great person and he likes to answer questions, so don't fear. I mean, when there's someone that you need to fear, we'll tell you, but or not. But in this case, really, start of the year, so we're starting by encouraging many of the students, and we ask questions anyway. So do that, and of course, I mean, don't start moving now, but next time, feel free to sit a bit closer. I'm not sure, I mean, maybe the acoustics is great and you can hear him, but you know, up to you. So, welcome to the Physics Colloquium of this year. And today we have Adar Steinberg from the Hebrew University. He finished his PhD in 2007 in the Weizmann Institute in Tamir Yaakov, working on 1D systems. Yeah. And then I did a 2-year postdoc in Jerusalem, where I met him. He was working with Oded Milo and Banin on colloidal systems. And after a postdoc at Harvard, at MIT, sorry, with Pablo Calero, working on the vast materials and 2D systems and topological insulators. He started his position in the Hebrew University in 2013 and kept on working on these types of 2D systems, stacking systems. He's an expert in these issues, working on both using them for sensors, which I don't think he's going to talk about today, and various quantum properties, such as using seeing defects as through tunneling effects and learning about their properties, which is part of what he'll talk about today. So without further ado, Adar, thank you for coming. The stage is yours.
Thank you, Amos, and it's always a pleasure to come here. I haven't been here for a very long time, and I almost couldn't find the way because the whole environment has changed. It's been there's a complete upheaval, as you probably noticed. So today I will share with you some of our recent experimental work. Now, work has been taking more and more focus recently towards the use of defects inside the layered materials. And basically, what you see here is just these little pastoral images of rocks, stepping stones inside the river. I'm going to show you that we're going to exploit nanometric structures, namely defects within very, very thin layers, to see how electronic transport is carried out through such hopping properties within these very, very thin materials. And specifically, I'm going to show how we can use them as various kinds of sensors within these 2D systems. Now, to see which direction is forward with this. Working, yeah. Forward, backward. Well, this is going to work. Oh, I think the computer is stuck. Okay. This? Okay. Maybe. Okay, good. Okay, so this work is done in my lab by a series of PhD students and postdocs from Dvir, Itai Keren, Davidas, who's right here, Ayelet Salik, and Shachar Simon. And some of the results I'm going to show you are a product of a long-standing collaboration I have with a group of Marco Aprili and Karis Quay in Marseille. And numerous people have assisted with theory, Maxim Chodas and his group, and the group of Yuga Maya. Again, this has to be, doesn't simply work like that. Okay, so the executive summary, what you have to remember if you fall asleep right now, is that we study layered materials, and within these layered materials, there are defects, and we have ways of constructing structures which involve graphene as a source electrode, where tunneling takes place through a defect in this very, very thin barrier, and we can use these defects in transport experiments. We can use these defects to couple to superconductors. We can use these defects as a local sensor, and these defects can be capacitively coupled to gate. Basically, we have the full functionality of a tunable transistor within a single atomic defect. Now it works. So the talk outline is going to be as follows. I'm going to introduce quantum dots, and I'm assuming that there is no prior knowledge of quantum dots in most of the crowd. There are some experts here, but many of you will perhaps meet the quantum dot here for the first time. So I'm going to assume that. Yeah. Yes. I don't think not of a single atom, not of a single atom, not of a single atom. Maybe 6 nanometers, 10 nanometers, but it's not a single atom. That's about 40 atoms in terms of nanoscale logic. So I'm going to introduce layer superconductors, which are going to be part of the systems I'm going to be talking about. I'm going to show how defect dots couple to superconductor, what happens when they do. And then I'm going to show work done by Devidas of spectroscopy using a defect, energy spectroscopy of a superconductor using a defect. And finally, I'm going to show how we can use carry out very sensitive electric field sensing using a defect, which resides next to graphene. So first, I'm going to give a brief introduction into quantum dots, what they are and where we can find them. And I like starting my talks by acknowledging my academic hero. This is Ivar Giaver. Ivar Giaver earned his academic fame by inventing devices based on tunnel junctions. He worked in, he's Norwegian. He worked in the labs of General Electric in Schenectady, New York in the 1950s. And he tried to build a tunnel device. And I think it's a good read to read his Nobel Prize lecture where he says, we tried to keep two metals apart by using a variety of thin film insulators. We spent some time measuring very interesting, but always non-reproducible current voltage characteristics, which we refer to as miracles. They tried various things. They didn't work out until they hit the correct method. The correct method is the method that everybody uses till this day. This method is using the physics of oxidized aluminum. What they did is the following thing. They used an evaporator, which is basically a vacuum chamber. They evaporated aluminum, and then if you evaporate an aluminum strip and very controllably introduce a small quantity of oxygen into your chamber, you have a thin layer of oxide. The special property of aluminum oxide is that it envelops the entire layer of aluminum, and it is a very clean, very homogeneous oxide layer. And eventually what he did was use some kind of a mask to create one layer, oxidize it, then create another layer. And then he has this tunnel junction which exists between these two layers. And then what he did was deposit aluminum and lead. Lead is a superconductor below 7K. Aluminum is a superconductor below 1K, but at the level, at the temperatures that he measured, aluminum is a normal metal. So what he got is a follow structure, which is very commonly used today. It's called normal insulator superconductor junction. And essentially what you have here is the situation of this is a superconductor, it has this energy gap. That's a very prominent part of superconductor physics. What Giaver assumed was that if he tries to tunnel through a barrier into the energy gap, he's going to see the energy gap. The nice part of the story is that when he shared this idea with theorists, they told him it's not going to work. So you don't have to understand, young man, the superconducting gap is not a gap in the density of states in the sense that you understand it. It's not going to work. He didn't listen to them. He tried and he succeeded. And what he saw was that the current voltage characteristics have a suppression around 0. And if you take a derivative, you get this function, which is a smeared version of the famous BCS density of states function. And that was the first measurement, direct measurement of the superconductor density of states. And that earned him the Nobel Prize in Physics in 1973, which he shared with Brian Josephson and Leo Saki. Now, these tunnel barriers, these oxide-based tunnel barriers are real workhorse. Till this day, almost everybody does quantum information based on superconductors, and you have labs like that all around now. They use the same aluminum oxide tunnel barrier technique. And if you want to isolate small regions like quantum dot, you also use the same technique. And that's what I'm going to show you next, because Giaver invented this technique in the late 1950s. By the 1960s, many people were building various devices based on tunnel barriers. And it's an early technology, so many of the barriers were defective. And what they saw when they were measured defective barriers, that they said in these various papers by Rowell and Shen and others, if the oxide layer contains states through which the tunneling electron can scatter, then anomalies can occur. Basically, they say, okay, it's very nice that there's a technique to make tunnel barriers, but in the 1960s, this technique was imperfect. So they were very, very sensitive to defects in the barrier. And in the later work by Giaver himself, also in the 1960s, you see the following drawing. You're going to see this drawing again soon, but what you have here are energy levels of defects inside the barrier. And he shows you there could be hopping between the Fermi function into allowed states within the barrier and then to the subsequent metal. And this is the first generation of quantum dots, are dots within barriers, which were grown in the 1960s. Now, what you have if you turn the clock forward, in the late 1980s, you start seeing more refinement of quantum dot physics. Here, there's this very, very famous work by Udi Merav, who was an Israeli postdoc working with Mark Kastner and Shalom Vind in MIT in late 1980s. And what he showed is that you take a two-dimensional electron gas, basically a layer of conducting electrons, and you pattern very cleanly defined gates, metallic gates on top. You can isolate this region here. And if you try to tune the density, you see this oscillation, these oscillations in current. And these oscillations come from subsequent charging of this localized region. And further refinement you see in the late 1990s, and that's one of the canonical works in condensed matter physics. It was done by David Gulhaber-Gordon, now in Stanford. He came to visit the Weizmann Institute, and this fabrication was done in Weizmann Institute. That's again, it's a two-dimensional electron gas, and that's a quantum dot which is isolated using metallic electrodes. And another method which was also developed in the 1990s, this work, I think, from the Max Planck Institute. They deposit aluminum. They let the aluminum oxidize the same way that Giaver did 30 years earlier, and they deposit subsequently without ever breaking vacuum these two source and drain electrodes, and then they have the following structure: a source, a dot, a drain, and a gate. Now this is a very important schematic. It shows us that there's an isolated region in space where you can add or subtract charge. This isolated region is capacitively coupled to a source and drain electrode. It is capacitively coupled to a drain, but you can also, there is a very small tunneling probability, which may or may not be tunable, from the source onto the dot and from the dot onto the drain. So essentially you can drive current here, and this current takes place through individual hopping of electrons on and off this quantum dot. Now, everything I've shown you so far is an ever refined techniques to create these quantum dot structures that by the late 1990s were already quite refined and give quite good control over geometry.
So this dot, if I see correctly, is 8 millimeters.
This here, that's no. This is about 500, half a micron. This is, I think, about 100 nanometers or so.
We're 8 millimeters. Well, never mind. So what is the definition?
8 millimeter is something. This is not the bar. The bar is 100. 8 millimeters, probably the aperture of the beam or something.
What is the size? What is a dot? Because how small it has to be a dot? Or,
it can be pretty big. It can be a micron. It can be a few microns. The dot. So it's a good. So it's good that you asked me. A dot is a region in space which is weakly coupled to its environment, where energies are dominated by capacitance. Now, for energy to be dominated by capacitance, in one slide, I'm going to show you what it means in terms of energy and temperature.
But not space.
No, not space. It can be pretty big. It could be a few microns. It can be one atom. It can be a few microns. Yeah, thank you. Okay, so what you have, if you look at tunneling, transport through dots, is that transport is carried out by single charge tunneling events. And part of the properties of dots is that they permit charge to go through only by single charge tunneling events. And the reason for that is, if you replace this picture by this picture, is that it's very difficult to put two kids on one stone. You can do that, but it costs a lot of energy and mass, and sometimes they fall into the water. But as you see here, generally you have one kid per one rock, and in electrons, with electrons the same, and the reasons are capacitive energy. The thing about these quantum dots is that the capacitive energy Q square over 2C is, because C grows so small, the capacitive energy grows so large, it becomes the dominant energy scale of the system. That means it's going to be greater than temperature, greater than most significantly greater than the confinement energies, the solution of the particle in the box, the orbital energies. So you are dominated by this capacitive energy. And what this means now is that you can make the following drawing, and this graphical drawing is what I'm going to be using for the rest of the talk here. You have these energies of adding one dot, and the difference between energy adding electrons to single electrons to this dot are E²/2c per addition of a single electron. That's the price of adding subsequent electrons. That's called the Coulomb ladder. And the distance here, E²/2c, is going to be greater than the smearing due to temperature. It's significantly greater due to variations due to the quantum confinement. So now if I want to ask the question of whether or not I'm going to have transport through such a dot, I have to create this graphical representation that asks whether or not this very sharp energy level is or isn't resonant with the source and drain electrons. And if it's resonant, you're going to have transport. If it's not resonant, you're not going to have transport because there's not sufficient energy of an electron coming from here to reach, to populate this level and come out. That regime is called the Coulomb blockaded regime. There's insufficient energy to add electron into the dot. Now, what I'm showing you now has been kind of common staple in condensed matter talks about 20 years ago. Anybody who grew in my generation saw that twice a week. Now, I'm assuming that I'm trying to be a bit pedagogical here because I'm assuming some of you have never seen this before. What you have is the following situation. You look at the gate, which is an electrode tuning these energy levels up and down, and you look at the bias, which is tuning the source versus the drain, and you ask whether or not you have current. Now, you can tune the gate, reach this resonant condition, and this means that now in this bias versus gate space, you're going to have current under these exactly at this gate level. But you can further tune the gate and you tune into the Coulomb regime again. So you lose your current. So you can't, if you sweep the gate here, you're going to see an onset and offset of electrical current. Now, you can do the same thing with bias. You start applying bias and you reach this level. But now you have to remember something important. All these source and drain electrodes have huge capacitances of your own, so the energy is going to run away from you. So if you calculate everything correctly, you're going to find that there is a condition where the source catches up with this available resonant level. And that means that, of course, if you apply positive bias means negative energy. And again, you have an onset condition of current. And you can easily show that there is a diagonal, which is an onset condition where this resonant level is resonant with the source. We call this the source onset condition. This is a condition where the source catches up with the available energy level. You can also show that there is a drain resonant condition where current goes backwards through an energy level resonant with the drain. And now you have these two diagonals, zero current here, and positive current on this side, negative current on this side. And this shape, it's called a Coulomb diamond. This and the slopes here, the source onset slope and the drain onset slopes, are determined by the capacitances in the system. That means that once you've measured everything and you see these diagonal lines in your measurement, you can actually determine one-to-one, you can determine the capacitances in the system. And that kind of curve, which is differential conductance versus gate and bias, showing you the shape of like hourglass or diamonds, that's a very, very common curve. These are called Coulomb diamonds. And if you see them, you know you have a relatively well-behaved quantum dot. So per your question, a quantum dot means that your temperature is smaller than the Coulomb charging energy. And if you can see this kind of resonant behavior, it means that you're in the single charge transport regime. Now, these are quantum dots.
I would argue that you have to have the biggest system.
What is it?
I believe that you need to have a relatively large system. Because
no, you can have this on a very, very small. This data was measured on a single molecule, on a C60 molecule. So it can be
because when you have these two, the drain and the source, if you have one electron there on the tip, or some charge or some molecule that is moving there, it will be so sensitive to that. So
it will. That's why it's such a very, very sensitive sensor. But if it's a good metal, even if they're turned around,
the picture is breaking down now because you don't have these very clean energy levels because you have some chupchik coming there and disturbing it. I mean, it's so unstable that
actually, well, whether it's stable or not depends on its environment. It can be made very first, and also depending on most of these measurements are done at very, very low temperatures. So things tend to go more stable because a lot of these fluctuations are quenched. But
then each dot will be different. I mean, because each dot will have some quenched environment or whatever.
Well, okay, so you're right because but there's 50 years of know-how of people who work with these quantum dots. So, for example, people who work with gallium arsenide, they have developed these working methods of how to cool down the dots in such a way as to quench away a lot of the dirt. And if you work in gallium arsenide, it's a very, very clean system. With molecular physics, it's much more complicated because they have a single molecule, which is indeed a very, very dirty environment. And I'm going to show also that with defects, the environment is actually pretty clean because it's a single defect where there's not much around it. But you're sort of, again, you're helping me here because what you're claiming is that these dots are extremely sensitive to the environment. And what I'm going to claim next is these dots are very, very good sensors. They're very, very good sensors because they are extremely sensitive to their environment. And if we look at why are dots very, very good sensors, I'm going to give you three examples. One is that if you look at the transport through this resonant level, if we can tune this resonant level up and down, I have a very, very sensitive spectrometer. And a very, very sensitive spectrometer, that's, for example, that's a very famous paper from the group of Charlie Marcus on a nanowire where there's a dot defined here at the edge of the nanowire. And I'm not going to go into the whole story of Majorana physics to which this experiment belongs, but my example here is the dot here serves as a very, very sensitive spectrometer to the physics within the rest of this nanowire. But a dot is not only a spectrometer, it can also be a thermometer because the transport through the dot is dominated, if everything is good and everything is quiet and everything is stable, transport through the dot is dominated by the thermal smearing of the source and the drain. And therefore you actually measure the temperature. And this is work by the group of Amir Yacobi, and where he measures the temperature of quantum hole edges and uses these quantum dots defined within the gate defined within the 2D gallium arsenide as thermometers for heat flow within the quantum hole edges. A dot can also be used as an electrometer, meaning that it's very sensitive to electric fields. So if I scan the gate here and I get these on and off current signatures going through the dot, that's work done by by von Klitzing's group in Max Planck. And then you can see that these signatures, this Coulomb ladder goes up and down, depending on the electrical environment. That was the first measurement of the quantum Hall system, how electric field around the quantum Hall system evolves using a very sensitive quantum dot called a single electron transistor, defined patterned above the 2D system. This has been refined again by Amir Yacobi and then by Shachar Ilani as a scanning SCT system, which is basically an extremely sensitive electrometer to anything that you can engage close by. And I want to point out the distances here. Typically, a quantum Hall system is 50 to 100 nanometers deep. That means that this device, which is patterned at the top, is 50 to 100 nanometers from the target system. So we have something interesting we want to measure, and we can deploy the very, very sensitive sensor 50 to 100 nanometers away from whichever it is we're trying to measure. And now I'm going to reach my actual motivation. My actual motivation is to see if we can develop a quantum dot sensor, which will be small, and I mean the smallest thing object I can think about is a single atom. Generic meaning I wanted to address many kinds of different systems. I want to have a tunable energy, meaning that I want to tune these Coulomb ladder states up and down. I want to be able to deploy it close by to another system. I told you before that 50 nanometers is a good benchmark which was reached over 20 years ago by the quantum Hall community. And I want to have a control over where the dot is positioned. I'm going to argue the defects within these van der Waals stacked materials are a good type of such quantum dot sensor.
So in order to tune the dot energy, what we do is changing the capacity of the source and the drain.
What I need is so the source and the drain, by applying voltage on the source and the drain, the dot energy evolves up and down, but you need a third knob. You need another electrode which is just capacitively coupled. That's called the gate. So this gate tunes the energy up and down independent from the source of the grid. But that gives you this very important additional degree of freedom for sensing. Now, so that's my whole animation claim that I skipped. Claiming that all this list of properties that I need: small, generic, tunable, energy, and deployable. And let's see what can help us. For example, this study from the group of Paul McEwen used the C60 molecule as a single quantum dot. C60 molecules are pretty small. The problem is this system is very unstable. It's very, very hard to fabricate. It is prone to dirt. It would not survive for a long time. And you cannot deploy it very easily on a large variety of systems. You can also build quantum dots within graphene. That's a work by the group of Klaus Enslin in the ETH. So they take bilayer graphene, they pattern it, bilayer graphene can be gapped. This means that you can create a quantum dot using gates, and they see very well behaved Coulomb diamonds. So it's a very well behaved quantum dot and can be a very good spectrometer, but it's not generic because it can probe graphene because it's part of graphene. So I want a quantum dot which would be generic, which would be able to couple to many kinds of systems. So here I say I want to use defects. So the van der Waals materials, which can be exfoliated very, very nicely, very cleanly by using Scotch tape, are relatively very clean materials. But if you look very closely, you see that you can have various kinds of defects. For example, this is molybdenum disulfide, and these are various kinds of crystallographic anti-side defects in the lattice seen by Tillian. It's becoming very, very popular right now to also use fluorescence to study these defects. The group of Igor Aronovich in Sydney is one of the group world leaders. So they look at various kinds of defects in hexagonal boron nitride, which is also a layered insulator. They see the fluorescent signals, and they ask and the question is whether this kind of defect can serve also as a defect which can be addressed in electronic transport. And the answer is, if we can do that and you can have transport through such a defect, it is small because the dimension is atomic. It is generic because it means I can couple to any conductor that can be onto which I can deploy the insulator carrying defect. The energy is tunable, and I'm going to show you how by a technique which we developed in our lab. And it can be deployed very close to the target system, about 1 nanometer away. So if before I had SCTs which were 50 nanometers away, in the quantum Hall systems, here I have an SCT, single electron transistor, which is 1 nanometer away from whichever target system I would like to deploy. What is my time frame here? We started at 10:45, so it's about 11:30. Yeah. Okay, good. Good.
So can you explain what is the source? What is the gate? What is the drain?
I will explain. Oh. And this arrangement, I will explain multiple times.
Okay.
Okay. Good. Yes.
Defects in a 2D structure or defects in a 3D structure?
So these structures are pseudo 2D, means they are layered structures. They are very, very thin. And typically we call them 2D because we never go beyond 2 nanometers thickness, although they sometimes have 2, 3, 4, 5, 6 layers. But you decide if you call it a 3D or 2D. It's a single defect within a layered material, 3, 4, 5 nanometers thick. 3, 4, 5 layers thick. Okay.
Can I ask you another question?
Yes.
You really explain nicely that the energy is related to the charging.
Yes.
But if you have such a small system, like a particle in a very small sphere, you also have energy levels of a single electron,
right,
which are also quantized, and
right.
then they can be either in resonance with whatever. So how do you know that you are? It's a many-body thing, or is it a single particle thing?
Okay. Okay. So if you look at the if you look at the ground state is a ground state. Well, at the moment you start adding n carriers, it's a many-body thing. But you said correctly. I'm going to reach that. With these particular dots, the charging energy is absolutely enormous, so we never go beyond one. You do see excited states, you always see them. And it can also be used as an excited state spectrometer, but these are states of the dot. You can always see the excited states of the dot. You're going to see the examples. So you're going to see what they look like and whether or not you can use them and whether they can fit.
Okay, so what controls the charging energy? What controls the capacitance?
What controls capacitance, you can look at it classically. If you go very close, capacitance goes very high. So there's nothing more than that.
Just the distance between the gate and the dot?
Yes. It's a bit more complicated, but if you look at it classically, if you look at the smaller the dot, the closer the electrons, the capacitance, the total capacitance goes way higher. The bigger the dot, the smaller the capacitance. Good. So generically, I have the following structure. I have an insulator carrying defects. I have graphene and I have a gate electrode, and I'm going to show you how using this structure where the source electrode is graphene, electrons hop from graphene onto the dot and then to whichever conductor that I want, is actually a source drain gate geometry. And that's basically what I'm going to be talking for the rest of the talk. So before I get there, I'm going to go step by step into experimental results. And I'm going to start off with structures which are much more simple. This is a superconductor. This is a barrier. Here I have a tunneling electrode. And I'm going to show you first what happens if there are no defects in the barrier. And then we'll understand what happens if there are defects in the barrier. How do we know that we have defects in the barrier? So my group started off working on tunneling devices built by placing a very thin insulator on top of a layered superconductor. These are the early papers of the lab at the time. And the way we fabricate the devices are, we place a superconductor, for example, this is niobium diselenide. Then we place an insulator on top of a sacrificial transparent substrate. In this case, it's PDMS. We align the two underneath a microscope inside the glove box filled with argon, because these materials are sensitive. They're sensitive to air, they tend to oxidize. We engage them together, disengage the PDMS, and then we get the following structure. This is a superconductor. On top of the superconductor, we have an insulator. This is a drain electrode. This is a source electrode. And tunneling takes place in here. For example, this is a tunnel barrier. That's a simple NIS tunnel barrier like Giaver 60 years ago. The only difference, he used aluminum oxide. We use molybdenum disulfide. There's tons of things I can say about why is it good to use van der Waals materials as barriers. That's not the subject of this talk. One thing that my group learned in a hard, painful way is that you don't, question? No? You don't always get these materials to engage really well. So what you want to have the barrier engaging the superconductor very, very cleanly. And two van der Waals materials engaging is not a trivial thing. This, for example, this is a topological insulator with selenide. We try to build a tunneling device. This is a TEM cross-section, and they simply don't touch. It's like putting two pieces of paper one on top of the other, and there is no contact between them. So you cannot build a tunnel barrier if this is the situation, even though the TEM images are very, very pretty. Another example, which is another painful example, we tried to build a device with MOS2 on top of iron selenium telluride. It's a claimed to be a topological superconductor. What we get is a very ugly oxide magnetite here in the interface, a gap, and here's the tunnel barrier. Once again, that means that it's very, very hard to build a tunnel device this way. We need certain sets of materials which engage well together, and it looks like materials from the transition metal dicalcagonite family, like molybdenum disulfide, tantalum disulfide, engage very well. This is work of my student Shachar Simon. This is the superconductor tantalum disulfide. It's 4 layers thick. This is the tunnel barrier, molybdenum disulfide. And as you see, they're perfectly engaged. So that's as good as you can ever expect. That's atomic engagement with this very, very simple fabrication methodology of pressing these two materials one on top of the other. And this is an example of measurements we done on niobium diselenide, tantalum sulfide. These are tunneling measurements. That's what part of what most of what my group does is this kind of tunneling spectroscopy. And generally what we see is you see the superconducting gap. It's a well-behaved, it's called a hard gap property. That means that you only have tunneling. You don't have any other processes. That's important. Shira? Okay.
On which scale will they engage with? You have.
You saw them, these are atoms. What, laterally?
Yes.
Several hundreds of nanometers, as big as we can see. Hundreds of nanometers. We don't, this is a TM image. So with, as large as your TM image, it engages well. Of course, you go to the hundreds of nanometers, you start to see bubbles and dirt and stuff like that. So, but we can see the AFM with the bubble. We can see the TM at the tens of nanometers. Somewhere in between, you don't have a perfect on micron by micron. It's not micron by micron. What is it?
100 nanometers.
No, these are very, very good junctions. And one reason you can see if these are good junctions, you see that the superconducting density of states is very, very well reproduced by the tunnel junction. It's called hard gap. And if you can take the second derivative, you can see that the superconductor actually has two gaps. Now, remember this because I'm going to go back to this two gap property. The superconductor which we work with, niobium biselenide, has two gaps. And now I'm going to show you in 60 seconds everything my group did, which is unrelated to defects. We studied the two gaps of niobium biselenide, and we showed that if you apply an in-plane magnetic field, you can actually differentiate them. One evolves differently than the other because its kinematic properties are different. The carriers are different. We could identify that one gap is related to a certain band, the selenium band of this material, and the others are related to the niobium bands. The second thing we can do was carry out spectroscopy at the presence of superconducting vortices and measure the density of states of vortices. This is another paper by Tom Veal. We could, with a lot of effort, measure the topological superconductor iron telluride selenide and see that its gap survives even if you apply a very high field, probably because of sparsity of the vortex states. And we could measure this niobium biselenide at a high in-plane magnetic field. Niobium biselenide survives high in-plane magnetic field, and because of what I'm going to say later, it's important to understand why. And I'm going to say a few words about this transitional metal dicarbonate superconductors. It's a very, very hot topic today. Many people study that because these materials have a very strong spin orbit term. The result of this very strong spin orbit term is that electrons which propagate within niobium biselenide experience an effective magnetic field which locks the spins out of the plane. This means that if you look at a superconductor which has Cooper pairs, you have a spin orbital which very strongly stabilizes the Cooper pairs. And that's a very good thing because that means that you can apply a very high in-plane magnetic field and cannot destroy the superconductor. And that's been shown using transport measurements. And that's something that my group has been doing for some time, trying to build tunneling devices into this material, taking such a device to Grenoble, measuring up to 30 Tesla, and we are arguing between ourselves and with the referees of papers, why does the gap survive into such a high magnetic field? And some theory by my colleague Maxime Chodas claims that it becomes a triplet superconductor because you have these two spins and they are tilted in the plane, then you have this triplet component. Okay, so maybe it was more than 60 seconds, but that's everything we did, which does not involve defects. What happens if you do have defects? Now, remember, I said this material can survive, the superconductors can survive into very high in-plane field. That makes it possible to characterize the defects, and I'll show you why. So again, this is the structure, it's a superconductor, normal metal, and there's a defect in the barrier, and let's see what happens. We measure the spectrum and we see little squiggles in the transport way inside the gap. And if we look at the data and on a very thin niobium biselenide and we zoom very carefully, we see these subgap states. And now if you want to say something quantitative about these subgap states, we start applying an in-plane magnetic field. Luckily, since this gap is going to survive into a few Tesla, unlike layered deposit, non-layered superconductors, like the regular metallic superconductors, then what you get are these two features, and you see them splitting versus in-plane field here up to 3 Tesla. And the plus 1 minus 100 microvolt, and they meet somewhere around the 2 Tesla. Now, how do we know that this is a defect? The reason we know that this is a defect is that it's an almost a textbook reproduction of what you expect from a quantum dot coupled to a superconductor. Quantum dots coupled to superconductors have been studied quite extensively using nanowires. You have a nanowire and you can deposit an evaporated superconductor such as aluminum or niobium or vanadium. You can create dots and barriers. And what people saw is that this is a study, for example, from the group of Silvano Di Franceschi, is that you can see these states which are called Andreev-bound states. They are related to the fact that if you want to add carriers into a defect where it's a superconducting correlations are involved, then there's a singlet state and a doublet state, which can split under the effect of magnetic field. And at a finite magnetic field, there's a quantum phase transition, which appears here. Now, our data looks very, very similar to their data, and it is described theoretically by exactly the same model. This means that a defect within a barrier can be used as a rather sophisticated system of the quantum dot coupled to a superconductor. In some cases, it looks very much like a Majorana state. It's not a Majorana state, it's not topological, but it just looks like that. And in that sense that, although far less controlled in the sense of engineering, we can still get similar to physics to what people can reach with these quantum nanowires coupled to superconductors. Now, what happens if I want to actually tune the energy of this defect? And that brings me to the work that Davidas did before you stole him from me. And to be able to tune the energy of this dot, I need to use a graphene electrode. Okay.
So just understand the in-plane field that you apply. So if this is your layer, you're moving in this direction. Okay.
It's in plane. It's within the plane of the superconductor and the barrier.
Yes, attributed to you have a very, very, very small cross section. So actually, because it's just two-dimensional material.
It's not enough because then you have something called this. You mean the stability of the superconductor? Yeah. So it's rather, so in this sense, you'd have, for aluminum, for example, can survive a Tesla or two, you have something called the Pauli criteria. Pauli criteria tells you that the Zeeman splitting between the two Fermi surfaces eventually is going to kill superconductivity. Now, in TMD, that doesn't happen. You can reach 30 Tesla. And the reason you can reach 30 Tesla is the spin orbit coupling just locks the spins. Otherwise, Zeeman, you don't have the Zeeman, you just don't have the evolution of the Zeeman. Okay, now we have a defect. Now we want.
You say a defect. There could be many different types of defects. So
how do I know? How do I know?
What is the defect?
Okay.
What type of defect?
Okay, so what type of defect is, we usually don't know. We know that there is a defect, but we can tell if there's one or a few. In the next two slides, you'll see what happens when there's one or a few. Right now, the place where we stand, embarrassingly, is that we see their behavior in transport. We don't know what is their chemical identity. It's a vacancy or a dopant. We don't know where they are on the XY plane. We know where they are on the Z plane, but not on the XY plane. And that's kind of the challenge where we're facing right now, to take more control over this defect system. But what we know is that there is a certain probability of having such and such number of defects per square micron. So we can guess, fabricate, assuming there will be defects. And when David has fabricated his devices, there were defects. And what you get is the following situation. Now we get into the technique. So I'm actually running very short on time. So that's basically what I'm going to show until the end of my talk. How we can tune the energy of a defect using a graphene electrode. And the property we use is the fact that graphene is a conductor through which you can apply electric field. So look at this defect. I want to control the energy. I need to apply a gate. The way I deploy the gate using a gate electrode which resides behind the graphene source, where the field penetrates through graphene. Now, if this were just gold, I would apply voltage on a gate. If the defect here is between some source electrode and the drain, I apply a go voltage again, nothing would happen because I have screening. Graphene is a very, very poor screener. And the reason graphene is a very poor screener is if you apply voltage on a gate, it charges the graphene, pulls down the electrical potential, creates a chemical potential. So phi plus mu is V, V is voltage stays zero. So you can tune this dot energy up and down and switch the transport on and off. Basically, this means if you have a finite capacitance through graphene, you can actually measure this capacitance. And the device that Davidas built was built from graphene. On top of graphene, there was MOS2. And on top of MOS2 was NBSE2. So transport took place through graphene, tunneling through the MOS2 with a certain transport channel dominated by a single defect. And I'm going to show you how we know it was a single defect. That's a DIDV of the junction, looks very much like an album that's solenoid, but if we apply a gate underneath the graphene, we see that the DIDV changes. Now, we subtract this value of the average contribution of this of the tunneling junction. And what we get is something that looks very much like a Coulomb diamond with a gap in the middle. The gap in the middle is a superconducting gap. The reason is that if you're on resonance from the graphene source, you hop through the dot and you gap. So there's a certain range of forbidden energies. Now, what happens now if we take a high resolution scan of this measurement, we see that it's a very anomalous looking gap, and this line is kind of diffuse. And this is actually the spectrum of the superconductor. And the reason this is the spectrum of the superconductor is that if we tune this, along this trajectory, we actually tune the defect versus the energy of the superconductor up and down. And the reason you can see that is that along this trajectory, the dot is kind of in the Coulomb located region, it is forbidden. And along this trajectory, the dot is parallel to the source onset, which I defined before. That means you can tune the dot by sweeping it versus the energy of the superconductor, and therefore the transport along this trajectory is actually a measure of the superconductor density of states. So what we can tell now is that we measure the transport through the dot, and we see that there are two peaks. Now I told you before that niobium diselenide is a two-band superconductor. Now I can measure this two-band property directly, exploiting the fact that I have direct tunneling from graphene to the superconductor. If I take the second derivative, I see these two peaks here and here, 0.6 and 1.2 millielectron volt. But I also have indirect tunneling through the dot, which gives me the same two peaks at different intensities. That's a bit technical, but that's actually quite important because that shows that the dot couples to the same energy level, but at a different set of probabilities. That means that the dot undergoes some kind of a selection rule when it couples to the superconductor, and Davidas has spent a lot of work trying to figure out these selection rules, showing that the dot actually favors the lower energy band, which we know is a selenium band. Now, the one possibility is that the dot resides geographically just above a selenium atom, which is here. Another possibility is that in momentum space, these are the selenium levels over here, and since tunneling through a dot tunnels into the low momentum states, there's a momentum selection rule that favors these states over these states, which are at high momentum. We actually don't know because we have only a single dot. A third possibility is there's some kind of an orbital order related to the structure of the orbital of the defect. Now, here, this is not working very well. And if you switch on magnetic field, you fill this gap and you see the recovery of this Coulomb feature. Now, I see only one X. The fact that I see only one X means I have only one dot. Of course, you always have some devices where you have a few dots, but that particular device says you have over an entire junction, you have one single dot, which is as the spectrometer. Okay,
what is doublet C?
That doublet is, okay, that's the excited state of the dot. Now, the dot, if you apply magnetic field, the dot Zeeman splits. What you see is the Zeeman splitting of the dot, and you can actually extract the G factor of the dot and everything. So it's actually pretty straightforward to calculate. You just look at the energies of this Zeeman split state. Now, I think I'm out of time, right? Okay. So I'm going to skip a whole chapter about work of Itai Keren on graphene, which is basically showing that the dot can also be not only a spectrometer, but also an SET, being very, very sensitive to the states of graphene. And that's all of this animation I'm going to go through. And I'm going to reach my conclusion, my summary. My summary is going to take 2 or 3 slides here. I showed you that we have defects, and the defects are small because they're about an atomic state. They could be a bit larger because a defect state is not strictly atomic. It's a bit bigger than an atom. They're generic because they can put various kinds of conductors as long as they engage well with the barrier. The energy is tunable if I can use a graphene gate source through which I can gate the dot. I can deploy them very close to the desired system. And that's, since I didn't show you the graphene data, that's actually quite important because now you have an SET, which is 1 nanometer away from something else. That means it's extremely sensitive to small variations of the electric field. And there are various interesting things you can think about of what you can study if you have an SET, which is a nanometer away from something else. Superconductors or other things. Now, another thing we discovered, this dot is minimally invasive. It means it's not a metallic dot with all its screening and everything, which is half a micron big. It's an atom. So it cannot screen on its own. And it retains a planar geometry. So like an STM, which comes and locally disrupts the density of states and the electrical field. you have a planar geometry emanating from the fact that you have a relatively planar structure. What don't we have? We don't have control over position. Neither we nor anybody else right now knows how to create these dots, engineer them, and get them where you want. So how do people create dots? These are the techniques that by now people intentionally created defect states. Lasers, ion implantation, ion beams, plasma, electron beam, TEM, neutron radiation, mostly studied using optics, fluorescence. Now, we're in the stage of engineering, which is very primitive. We peel a piece of an insulator and we look for, we're like hunter-gatherers. You go into the forest with a nice mushroom, you eat the mushroom, you hope it's not poisonous. Now, we cannot grow the mushroom like in controlled agriculture. We cannot create these dots, but this is a technology which will be attained because many people are working on it and trying to reach it. Where do we want to reach? What people have managed, this is Igor Aronovich and Vladimir Diakonov, showed that you can look at these defects in hexagonal boronite and then tune them as quantum objects, as cold atoms or as NV centers, tune the quantum states using ODMR techniques or NMR techniques with microwave frequency, etc. Now, people did that with quantum dots using gallium arsenide. Now, the dream here is the fantasy is, can you do quantum control of a defect in the same way that people have done that? This is Jason Peta, still from his postdoc with Charlie Marcus. At the same toolbox people applied for gallium arsenide dots or nanowire dots. Can you do this with atomic dots? The benefits are huge because you have a quantum sensor, which is atomic in dimensions, 1 nanometer away from the system. It's very sensitive, very close. I don't know if it's possible, but it would be nice to try. And that's it. So I'm sorry if I'm right, but
so we have time for questions. Yeah.
Thank you for your time. So, I just have a question, like, why would certain materials go to one another?
we don't know, but we have by now a relatively extensive library of what sticks and what doesn't. And the rule is graphene sticks to everything mostly. TMD stick well to one another. Everything they control, iron controls iron. Next question. doesn't engage well with van der Waals. We are trying various tricks with maybe pressing them down with an AFM. If we manage, it will be really good because there are very, very interesting materials that you can study, or all these iron-based superconductors, iron-based ferromagnets. Right now, there are tons of papers of people building devices and showing, wow, we put chromium germanium telluride and we put on the niobium. They don't know that they don't engage. They didn't do the cross sections. They actually checked for the field, but they don't engage. You can, but you would like to have them controlled. Okay, 2 nanometers of vacuum is still enough that you can have tunneling, but vacuum has a relatively big gap. But you would like to have, you don't want to have this part of your engineering.
No question. To show you the features of your door, you use normal insulator superconductor junction, and then you have to filter out the density of state of the superconductor.
Not always, because
why don't you use normal insulator normally?
I can, because for the benefit of sticking within my time limits, I didn't show you data where I actually do that, but because you asked the question, so you are going to be punished by looking at this data. This is graphene, HBN graphite, no superconductor. There are actually few defects, but I'm showing only one. So if I tune the gate, I see this cross is from a single dot. These are excited states at about 50 and 70 millivolts. So these are excited states of the dot. There are other dots, but that's a single dot. And so that's measured for K. So that's a relatively elevated temperature. And the slopes here are actually a measure of the capacitance, it's actually a measure of the density of states of graphene. And that's something which worked a lot to prove, how to prove that. If it's just a simple gating, you'd have 2 straight lines, but this line is crooked because the density of states of graphene varies as the gate. So the answer is yes, of course. It's not a superconductor. Then I don't have to photograph it. By the way, that particular device that David has built, the barrier is relatively thin. We try to build devices with thicker barriers. If you have thick barriers, you suppress the direct tunneling and you remain with the dot-assisted tunneling, and then that problem would not occur.
And you start thinking, or someone else, on the current versus time in such a way that the electron is moving so slowly that you can see one electron at a time, or at least the noise should be very peculiar for this process.
Okay. So single electron transfer to dots on the time domain was already done by conventional dots, for example, in gallium arsenide, and there are very nice works by some people, one thing tell it doesn't matter. They put a sensor near the dot, and then they see the on-off, like charging, discharging, charging, and then they measure transport currents of femtoamps or attoamps, basically meaning looking at millisecond or tens of millisecond on-off transitions of the electrons hopping on and off the dot. So you can definitely do that if you have a sensor which measures the dot from the outside. And that's been done by bigger dots, which can be packaged and packaged on sensor near the dot. Noise was done like Moti Heiblum, Weizmann Institute, many people. Noise through dot is a big thing. And then you have bunching and anti-bunching and all sorts of physics, mostly in the quantum Bohr regime. But the physics of noise is non-trivial because you have, it reflects many body effects in the leads. So that's, of course, it's measuring these dots on the time domain is actually something which could be very, very useful.
What is the plan for the vision of this this technique? I mean, what kind of interesting physics?
So there's so there's certain things that if you look at my friends who do scanning SCT systems, it's something that they can measure anything down to as close as they can get their tip to the surface. Now, what system could, for example, one very interesting system for a time I student, for example, we're trying to look at vortices. Superconducting vortices are supposed to have charge. Now, it's virtually impossible to measure the charge using any other technique because the vortex size is about a few nanometers.
So it's really local, you're hoping to see.
Yes, I hope to see local variations of electric field because if my sensor is 100 nanometers away, everything's going to be washed up by the time, any local variation field is going to be washed up by the time I reach my sensor. But if I have my sensor deployed here, I can be sensitive to things bigger than the distance of the dot to the superconductor, any other system. But the distance is 1 nanometer. So that gives us some opportunities to look at physics at the sub 1 nanometer, sub 10 nanometer vision.
So can it also be used to study some kind of broken symmetry states?
Yes. So I'm going to show you later, not wasting everybody else's time, that we actually did that. We actually see broken symmetry states on graphene. And one thing that you can see, because the dot is very close, it can see the puddles in graphene because the compressible and incompressible strips move right next to it, and then it jumps up and down in energy depending on the charge structure within this compressible and incompressible strip. Now, it's very, very hard. Everything we've done on one dot that was measured by very, very high fields. But if with some more engineered control over these dots, one can look at like physics of quantum Bohr systems or 2D systems, again, because you can look at an energy scale, at a distance scale, which is closer, order of magnitude closer than the other SCTs. So yes, broken symmetry for the edge states, for example.
Like, I was thinking more along the line of, there are some exotic phases that can exist in quantum Bohr, like bond order.
Okay, no, I didn't think about that, but yeah. So anything that so that's.
This is very challenging.
Yeah. So the issue here is that basically you have something which is in spatial resolution is like an STM, but it cannot be scanned on X1. It can be scanned in energy, but it's far less destructive than an STM. Yeah, so there is an opportunity here. The engineering is difficult. You know, this data from 3 years ago, we have not reproduced another well-behaved dot on HBM because it's just the HBM is so clean that it carries very, very few dots, and we're bombarding it with electrons, and we're in plasma and everything. It's actually a significant challenge. What people start, there was a paper in archive today from Manchester that they intentionally contaminate the HBM before, and then we start seeing defects. There are more and more works on this vein, but
so there's more opportunities to talk about that today. That was finished. We're out of time. So thanks again, and thank you everybody.